Ladies and gentlemen, good morning. I must confess that I don't feel well today. I once thought I got this popular disease, but yeah, I made my test, hoping for the better. It's negative. All right, so I didn't have good excuse and I have to come to you. But just to be on the safe side, don't touch me today, okay? All right, so we are in the middle of our course. And what we will do today, we will quantize classical fields. After long preparation on the last lecture, when we exclusively dealt with classical fields, quantization by itself will be a piece of cake. We will go quickly through it, since we can quantize one oscillator, and we can do it in many ways. We can also quantize infinitely many oscillators which compose a field. Right, we can find the states of the field in terms of Fock states, but only Fock states. Right, we can talk about particles. It was quite a discovery that classical fields necessarily lead to particles. We had two examples, two basic examples of many. We've been talking about string, and there these particles are photons. And for electromagnetic field, these particles, you might make fun of me, but I constantly mix up photons and phonons. For strings, those are phonons, quantum of sound. And for electromagnetic field, as you know, as all you know, those are photons. Right. So we'll talk about most of them. Right. After that, we really come to, I would say, central relation of quantization. Actually, quantization in terms of creation and annihilation of operators is precisely the same for all things. To get physically significant, we have to make a link between operators, creation and annihilation operators, and actual physical quantity representing the field. We have to make it an operator of the field. That would be central relation, and that which would allow us to quantize the fields. In the second part of this lecture, we will look at, how can I say, manifestations of this quantization. There are things which come around. Those are 0 point fluctuations, 0 point energy accumulated in field oscillators. Those are uncertainty relations, similar to relations between momentum and coordinate, usual single particle quantum mechanics. And about quantum fluctuations of the fields, that all we will exemplify in the second half of this lecture. I guess I need to turn my mic. It should be better. All right. So let's start with all that. Harmonic oscillator. I guess you have seen it hundreds of times, at least in. Yes, please. We consider gravity we don't deal with gravity. The quantization of linear gravitational field can be done as we did in reality, most interesting cases of gravitational fields are not linear. For instance, one can think of quantum fluctuations consisting of black holes, such entities. The satisfactory quantum theory of gravitation with all these nonlinear effects has not been made yet. Something for you to but linear fields, as far as linear fields are concerned, if you consider weak gravitational waves, we can quantize it in precisely the same fashion.
How about just like Newtonian?
Hamiltonian?
Newtonian gravitation field.
Yeah, okay. Again, in linear approximation, one can write Hamiltonian for small variations of matrix. Matrix would cause some energy, matrix will propagate in space-time. Everything can be done in this interval. Fine. Right. It is again about single oscillator, which I write classically. We've been looking at classical oscillators for quite a time. A week ago. Right. So it's a Hamiltonian. And from classical Hamiltonian, I can immediately get equations of motion. That's not equations themselves, but yeah, it's a prescription how to make these equations. Just differentiating Hamiltonian with respect to momentum and coordinates. Good. That's classical mechanics. Now we're gonna make some logical jump. We want to assign heads to this quantities. So we will promote momentum and coordinate into operators. It's not enough, because if the operators, the action of this operator depends on the order of these operators. Classical mechanics cannot help in this respect. So we need to assume something about the way they be ordered, about commutation relations of these operators. And this, it's enough to postulate these relations. It's called canonical commutation relations. So on the left side, you have an operator, commutator of coordinate and momentum. And on the right side, we just have a constant, which appears to be Planck constant. This we mentioned. Fine. Then we do the following. We can write Heisenberg equations. Again, there is a prescription how to make equations of motion in Heisenberg equations. So we just need to compute an operator and the Hamiltonian of this system. Right. So we do this using commutation relations, and we reproduce the self-consistency is very important. It's closed loop. We reproduce classical equations in some limit. All right, that's most compact way to quantize harmonic oscillator. There are other ways. So here we used Heisenberg equation. A product alternative, which you use in your course of common quantum mechanics, usual quantum mechanics, is Schrödinger equation. That's a possibility. What we do this, but again, it is not handy. it is very complex to use Schrödinger equation in this context. Just if we will think about wave function of an oscillator, it will be very complex, having polynomials. I wouldn't even recall the form of this polynomials without looking into Wikipedia. Fortunately, there is a much more convenient and efficient approach to quantization. And that is to rewrite these operators, take linear combinations of those, if you make these operators and compute commutation relations, using again this postulate on the previous transparency, using this postulate, well, we reproduce the following commutation relations. And, well, if you're mathematically inclined, you've got a splendid idea, because these commutation relations are precisely as we derived for boson particles. That gets to a rather unusual idea. Any oscillator is a place where boson particles can live. All right, let me elaborate on this. Let me now treat the oscillator in terms of a level of the particles. So I rewrite the Hamiltonian in terms of operators and treat this in terms of creation and relation operators. It has the same form as a Hamiltonian for particles, which have energy h omega, omega being oscillation frequency of the oscillator. Fine, there is something extra, there's something extra, which is 0-point energy. All right, we will talk about this later. But apart from this constant energy, it is precisely as a Hamiltonian of particles, boson particles, which can be put into a single level with energy h omega, h bar omega. Fine, so we can put very many particles to there, increasing the energy. So all excited states of the oscillator can be seen as states with different number of particles. Ground state of the oscillator can be set for particles, it's vacuum. And all other states, as we also learned, particles can be created by applying creation operator n times, right? And normalizing the resulting wave function. Here we are. I also gave a formula for eigenenergies of the system, but that should not surprise you. It is just what comes about for non-interacting particles. Each particle has energy h bar omega, and all energies just add together. if particles won't interact, it won't be non-interacting, sorry, if particles would interact, we would have something more complex, which would correspond to non-linear oscillation. But as far as oscillators are linear, and again, it's important to understand that in classical mechanics, linear fields have very much of physical significance. They just describe small deviations from some equilibrium, right? Like steel ocean and small waves. If waves are big, you have difficulty, but small waves you can always describe as linear series. So linear series of classical fields can be directly mapped to series of non-interacting pulses. Okay, that was for one level. Now I just do copy and paste of my previous transparencies, changing singular into plural. So what we do this, because the field is not just a single oscillator, it's a plenty of oscillators. But quantization of a plenty of non-independent oscillators is just the same as quantization of one. So I rewrote everything. I hope I didn't make any mistakes. There's a set of oscillators. Each element of the set is a mode. It has its own coordinate, its own momentum. That's how equations of motion, classical equations of motion, are derived. If you do the algebra, you end up with linear equations, right? Fine. Now with quantize, we promote all these momenta and coordinates into operators. Simple promotion is not sufficient, right? As also in human society, right? You need to have something special, and that special is postulate of commutational relations. They're very simple and obvious. Operators commute if they belong to different oscillators, and for same oscillator, the commutator equals to IH bar. Fine, so that can be done for any number of oscillators. For operator algebra, again, it's all easy, it's all uniform. We just introduce separate creation and annihilation operators for each mode. So these operators by label K. Again, at this moment, it's arbitrary label. It could be in applications wave vector, discretized wave vector, but at the moment it is something which labels oscillators of the set. Good, and the commutation rules which we have for the operators. Just commutation rules of bosons. Yes, please.
In the A operators on top, we have an omega that does not have a subscript K. Is that relevant?
What is subscript? I guess it will have subscript K.
It's at the top omega Q.
Omega K. Oh.
In your formula there isn't a subscript.
I just don't get which formula do you mean.
For the creation and annihilation operators.
Yeah.
The omega in front of the Q operator does not have a subscript.
Ah, yeah, that's the idea. All right. let's put subscript. Let's put it. Fine. All right. So anyway, the idea is that you do it for each oscillator separately. Each oscillator has its own wavelengths. Very good. So again, we understand that any large set of oscillators can be seen as bosons, which can be in different modes, in different levels for the bosons. We rewrite it with rewrite the Hamiltonian with operators AK and a delta K, right? We again can associate excited states of each mode with the states with many particle states, right? Each time we add energy quantum to oscillator, we create a particle in this oscillator. Right. With vacuum common for all oscillators, it is defined in that unusual mathematical way, which can be expressed physically very neatly. You cannot annihilate anything in vacuum. If you try to annihilate, you just get a computer error. You don't get normalized wave function, normalizable wave function. You just get zero for any attempt to create to annihilate a particle in any mode. Right? Arbitrary state of the oscillator system is, as we learned, particles is an element of Fock space, which is characterized by occupation numbers of all K's in a row. Here we have it. Remember that it means n 0 and 1 and so on. Very long row of occupation numbers. Fine. So any state of this kind we can make by application of corresponding number of relation. We can all create. We can create straightforwardly all the states from that. Right. Eigenenergies, again, apart from this 1/2, which will be discussed later. It is the same formula as for boson particles. Good. So, in principle, I've done with this quantization. The only point I did it at so much abstract level, as a very easy one, that I don't have any physics. It looks like I have the same answers for any field. Well, I need to specify. Yeah, perhaps I would specify next page. But let us just understand where we are. It's indeed the middle of the course, some mid we have reached now, right? We have finished second quantization. We came to a summit where particles and fields is just the same, right? And we approach this summit from a valley taken to different hikes. First, we started with particles and went through examples to this summit. And 2 lecture and a half we have spent to achieve this summit, starting from classical fields. So at classical levels, particles and fields are very different things. At quantum level, they are all the same. Right, one can play fancy word games with classical and quantum. For instance, classical particles, that's where you start from. And if you start from this, the field is quantum object. But we could just play it other way around. We can start with classical fields. And in this case, the particles, the resulting particles will be quantum. But that makes sense if we are in the valley, if you think of quantum, classical physics. At quantum level, it's all the same. We don't have to make a difference. Fine. Right. That was kind of a subtle transparency of the whole course, also a bit philosophical. So let me go on and start with physical applications. Right. First of all, outline the goal in general way. And for this, let me remind that what we have done at classical level, what we did in the last lecture. We have started with some field operators. Again, A stands for arbitrary. It could be, for instance, operators of string displacement. Sorry, quantities characterizing string displacement or electric and magnetic fields, classical objects. We look on how do they move, which oscillators they form, and we have found normal coordinates for this oscillators by means of linear relations. Right? Then we went from normal coordinates to generalized momentum, generalized coordinate. And finally, at last step, we get to these expressions for AK, A deca K, and now we can make quantization very easily. Now we roll everything back. There is a chain of linear relations, and we're just gonna inverse these linear relations step by step. Okay, it could be cumbersome, but it's linear relations, it's all doable, right? So we start with operators, creation relation operators. We got operators of momentum and coordinate. Yet another step, we have operators for normal coordinates, and finally we get physical field operators. So, classical field becomes an operator, it gets quantized. Good, that's general. Let me exemplify it for photons. Did I get it? Right, yeah, photons in elastic string. Sure, what we know frequencies for each k, It's a sound-like spectrum, and we can associate wave vector is momentum of these photons. It's particles, so now it has a moment, a momentum, and the energy is h omega as expected. Right, so excitation, so this elastic string are photons, are particles. Right, so field operators, what I do here, I might use the expression for normal coordinates of this oscillator, which we have derived in the last lecture. Just substitute it. And as usual, when we go to applications, we encounter ugly square roots. That ugly square root contains all information about the relevant information about the string, its density per unit length, frequencies, everything. Right. It is still for given k, fields are convenient to regard as functions of coordinate time. So I just combine these expressions for all k's, and that's what I finally get. Displacement is an operator, and it's a linear combination of creation and annihilation operators in each quantized mode. You've got exponents, which look like wave functions of plane waves. With discrete case. Fine. I would like to immediately draw a simple but interesting conclusion from this expression. In classics, it's natural to have some stationary, or some finite deviation of displacement. Well, for instance, you could just tick the string with a finger. There will be some finite displacement. It will oscillate, right? If we think in terms of number states, in terms of certain number of oscillations, this state, similar state, is not readily reproduced. Eventually, for any state with a given number of particles, number state, the average of expectation value of displacement is 0. Who can explain me that using simple acts about creation and relation, which we can only simplify? Who can explain me why these averages are 0? Yeah?
If you put the U between flow states,
Yeah.
you only have like a single creation annihilation operator, so you don't get like that on the right side to get some.
So I have to apply it to a certain state, number state, and I have to come back to the same state.
Yeah, exactly.
So, but what I have in the middle either creates or annihilates. It always changes the number of particles. That's why the result is 0. Good. It poses an interesting problem, which we will discuss later in lecture number 9, when we talk about coherent states. At the moment, we understand that, well, number states don't suffice, so we need superpositions of the state to realize what we want. All right, that was about phonons in the string. I could talk more about phonons in solids. There's plenty of things I could talk about, but rather, the next step, I will concentrate on electromagnetic field. Because we also have, always have electromagnetic field, even in physical vacuum without any solids. Right, and then I want to tell you, which you already know, I could imagine that even in kindergarten, you have read something about this, about photonic disruptors, something like that. Transformers usually use such things. Good. Electromagnetic field in quantum language is a collection of photons. Those are excited state of magnetic field, of electromagnetic field, and those are particles. Now we can go a little bit scientifically. So where do they live? Where do we place these particles? These particles are in harmonic oscillators of the field, which are characterized by polarization, which can take two values, and certain wave vector. All right. And if we are talking about the state of the whole field, it's a quantum state, and that quantum state is being made in the basis of Fock space. It's been made from states which are characterized by a certain number of photons for each excited, for each mode, for each gate alpha. All right. So we have photons. It's still correct. It's just transparency. Yes, photons. So, if you look at it as particles, it becomes clear that photons have energy, h omega k, which for light is just ck, right? One can also compute momentum. Could, for instance, utilize the formula for Poynting vector or energy flow of electric field. So momentum as expected is like this, just h bar k. Right, if we recall our, when did you get relativity? I guess in the, was it everyday physics course? Where did you learn about relativity? I bet it was your first year. Which course was that?
Modern physics. Modern physics.
Okay, modern physics. Right, so if you recall modern physics course, we understand that it has to be relativistic in some case. And this formula is relativistic indeed. There's a relativistic relation between momentum and energy for particles without mass. So photons are massless particles from relativistic point of view. What we can say about statistics of bosons, well, just by derivation, they are bosons by construction. We made them from the field. Everything which we can made from classical fields are bosons. Right. Okay, here I had to correct the title, but it's okay. More interesting questions, a little bit confusing. I guess all these things which I told you, you have already known in some form. How about speed? From spin physics, which again is part of the course of common quantum mechanics, we know that spin particles with spin s can be in that many states. It's a number of spin projections. If of spin 1/2 for electrons, it's just 2. Then for spin 1, it's 3, and so on. It becomes bigger and bigger. The problem is that photons have 2 independent states for each k. So it looks like they don't fit this general classification. The explanation for this is that, rather fancy one, that photons in fact have spin 1. And in principle, they should have 3 possible projections. But they move too fast. They move with speed of light. So one cannot really, catch up a photon and look at it. If we would be able to do so, we would see 3 projections of its spin. But since we always move slower than photon, we only see 2 projections plus minus. Well, that's nothing to say. One needs to define quantization axis. But this quantization axis is readily set by propagation direction of this photon. So, in principle, they could be in the states with 3 projections, but these states are not observable in our world. Right, so a coordinate, talking about light, in general, the coordinate is not such a good idea. If you really think of classical geometric light without wave properties, the light is spread over a beam, over a line. I cannot really say in which point of the line this light exists. Well, we know where it is absorbed or reflected, that we know. But we cannot really catch individual particles of light, cannot really ascribe coordinates. So it is just not a good idea to use coordinates when describing the photons. It's too abstract. It's like this projection which has this idea. All right. Then what would be, it's again a little bit word equilibration, what would be classical limit for the photons, for any particles? That separates, if you recall relativistic physics, massive and massless particles. So for massive particles, relativistic limit is just something which we can touch. Metal, electrons, protons, neutrons. For massless particles, classical limit is fields. Something which we cannot touch, but that they affect the motion of charges, things like that, fields, waves, oscillations. All right, that was the story about photons. And right, I guess I will spend a minute to show you and to talk a bit about about rather ugly but very able formulas which actually express the quantization of electric field. So it's operator vector potential in terms of creation and annihilation operators of in all these modes. So at the square root, which to my disgust even contains a quantity which I hate, this the electric susceptibility of nothing. But anyway, if we use System International, it's there, it's in the right place. So this is the coefficient, right? And we have the separators. Polarization is encoded into polarization vector because its vector potential has to be three-dimensional vector. And the coordinate dependence for each k is encoded in these exponents. Right, so from this vector potential, we can make more physical quantities. We can get to operators of electric and magnetic field. So perhaps we can recall how do you do this. How to express electric field in terms of vector potential. That depends on the gauge. If we work in Coulomb gauge, then scalar potential is 0, and electric field is just, tell me roughly. Yeah?
Time derivative of the
Excellent, right. So it's time derivative of vector potential. So to get to this formula, I just differentiate it with respect to time. This goes to time dependence of creation annihilation operators. This time dependence is expressed like this. So look, I just have a factor of omega k in comparison with these two formulas. Good, I differentiate with this with respect to time. In order to get magnetic field, I do not differentiate with respect to time. I've got to do it with respect to coordinate. And it's not gradient, it's a funny thing which is called a curl. It's like vector product of gradient acting on A. Good. I applied here. I found coordinate dependence. So differentiation would just give me this vector K. Look, I have found this vector product. So here we are. Here we're done. We express electric and magnetic fields in terms of creation and annihilation. Good. Let's have 5 minutes break. Very good. So let us. We have derived everything which we. Yes?
unrelated to what is related to the equation. We make the Coulomb gauge for the vector potential. in the H1, so it doesn't matter.
That's right.
But after you go, I heard about that.
Yeah.
So current is affected by gauge in this experiment.
No, that's not a correct statement. It is not affected by the gauge. A run-of-bomb effect is still gauge invariant. It is so that in a run-of-bomb effect, there is a measurable effect on electron dynamics without the field. One can imagine the situation when there is no magnetic field, but say electrons go around a magnetic coil, never getting inside the coil where magnetic field is concentrated. Nevertheless, there is measurable effect on their dynamics, interference of electrons, or even a single electron. However, it is gauge invariant. Good. So what I wanted to talk about these three things: zero-point energy, uncertainties, and quantum fluctuations of the field, which, as we will see in 20 minutes, are very simple. Just about these lectures. However, there's some flavor of mystery related to these quantities. So let me explain. Sorry, I don't know why they have such a mystery flavor, but I can tell you some manifestations. Good. So, at some stage when I have changed my course, I also have been looking at the ultimate source of human knowledge, which is Wikipedia. And surprisingly, to my really greatest surprise, I found very reasonable articles about advanced quantum mechanics, second quantization, at this Wikipedia, which was quite a level above what they usually write about physics. Usually the articles about physics, they could be correct with respect to facts, but interpretation is just very strange. But there was a series of very good articles about second quantization. So I was surprised, I was curious who wrote these articles. I could have no time for that. So it was not obvious how to trace these people. I could find it by analysis of citations, extra literature, which they give in this Wikipedia articles. That's why I have discovered almost classified private research unit based in Pasadena, California, which have its private financing, so the aim can be anything. The aim was to investigate novel means of propulsion by using zero-point fluctuations of electromagnetic field. Good, so these guys have been given, I believe, as a general salary for this research, but perhaps the research didn't go so well, so they got plenty of time to write high-level articles for Wikipedia. Right, good. Propulsion. I would not talk about propulsion, but indeed there are some strange unsolvable puzzles related to zero-point energy. Let's go for this. First of all, it's very simple concept. Zero-point energy you see in any oscillator when you try to quantize it. Even the first oscillator you look at, you have treated it at the level of shrink equation. And what has been discovered, rather simple thing. Right, if I just sketch this oscillator, it's a parabol, it's a parabolic potential. So I expect that ground state has zero energy just at the bottom of the potential. But it's a quantum particle. It could not be squeezed to the state with zero coordinate, right? So quantum particle is spread around zero, and as such, it acquires finite energy, which happens to be precisely 1/2 of energy difference between oscillator levels. This is called zero-point energy. Right, so my question, which perhaps already implies the answer, can we use it? Can we just extract this energy from vacuum? Some energy, but don't you just abandon oil developments and just extract energy immediately from vacuum without much pollution? I would know how to pollute vacuum because it's a rather green process. Fine. We can explain why we cannot use this energy.
When you excite a particle, you then, and it goes back to the lower state, the energy you can use is about the difference. But if you're in the ground state, you're not able to.
Precisely. We can use only energy differences, right? So we cannot eventually get this energy without destroying the oscillator. Like that we cannot do. We don't know how to reduce number of discrete cases in our space, for instance. So, yeah?
Those studies indicate that energy is also a non-physical variable. That we can only measure differences in energy and not energy.
Yeah, so in principle one could add an arbitrary constant. But I have already fixed this because I count the energies from the bottom of oscillator potential, so that energy is zero. I have already fixed the reference point of the energy. Nevertheless, there's some extra energy. And indeed, if I, just take this parabola and make it straight, okay? Then this energy would change. I could extract it. Okay. But we cannot do it with oscillators of vacuum, right? But okay, even if we cannot do it, let us just count how much energy we could extract. Let me compute this for vacuum of electromagnetic field. Right, so what do I need to have to do? Well, just sum up all 0-point energies over all possible case and polarizations. I could rewrite this big sum as an integral, you know that. In this case, which I would have volume in front of it. That's okay, that's physical. Energy would be proportional to the volume of the whole space. But that diverges at big K. This integral is infinity. Okay, I can rewrite it in terms of frequencies, going from changing integration variable from k to frequency, then it diverges at big frequencies. At any rate, it's not only the energy, which is infinite, it is also energy per unit volume, which is infinite. All right, infinity. But since we cannot make use of this infinity, we could perhaps safely forget about this and just say, well, it's not available for us. But that was this strange guy, Albert Einstein, which taught us something very important, which has to be put in this context. Right? What he told us, I also believe that you got it in kindergarten. Does it look familiar? Fine. Each energy corresponds to some mass. This zero-point energy accumulated in the oscillators of electromagnetic field in principle would produce mass, which is uniformly distributed in all points of our space. All right. So we are inside of a bubble of massive body, in fact. And gravitational forces must have been overwhelming. They would squeeze us like insects in a split of seconds. So how do we survive? Strangely enough, that this question, which is, as I put, is rather fundamental, and persists for about 100 years without any satisfactory answer. We still don't know, despite of all this fancy theoretical developments, we still do not know why zero-point energy does not produce the mass, or why this mass doesn't produce gravitational field. Okay, that we cannot sort out. Let's concentrate, since we are engineers, on things which we can sort out. We cannot change physical vacuums, that's for sure. We are not gods yet. What we can do is to change the vacuum which we have in hands. Simple example. We replace a vacuum with some transparent crystal, which has finite dielectric susceptibility. Now I make it kind of relative to epsilon naught. So in this unit, the susceptibility of vacuum is 1. So what did I do thereby? I have changed the velocities of all photons in my medium. All right, I have changed the vacuum. I can modify zero-point energies. Okay. I have an idea that perhaps I cannot do it for all frequencies for all photons. Why is it so? Because what I did, I just filled vacuum with atoms. Atoms are some objects which have some response time. They would not respond on field which oscillates at frequencies much bigger than the typical frequency of atoms, right? Which is about 10 electron volts, something like that. in energy units. So that gives me an idea that I can modify vacuum in such a way up to certain frequency. Let me call it omega c. It is of the order of atomic energy. All right. Then one can compute how much 0-point energy I can have here. Right. So how did I get to this? Well, I just basically took this integral. But I've taken a difference between the vacuum which I created and physical vacuum. And I take this integral in finite limits. Good. This is energy density, which is in 0-point fluctuations. Fine. So I wanna compare it with something, right? I wanna understand the scale of this, if it is small or big. Fine. So how can I do this? I can take the scale of atomic energy. Okay. It contains atomic radius, right? So I also have a volume for each atom from this radius. So basically, I want to take the ratio of this energy at atomic volume to atomic energy. That's going to be dimensionless quantity. All right. We can manage this. I could skip all coefficients because they're not important, or whatever, choose it in the way I like, because it's order of value estimation. Right. And after 2 minutes of algebra, I end up with this. So the energy, it's atomic energy times some expression, which is made exclusively from fundamental constants, from electron charge and the speed of light. That quantity to the power 3. That quantity is one of most fundamental quantities in our world, at least from the point of quantum physics, so that it's called alpha. But it has kind of rather strange name. Who knows the name? Fine structure constant, precisely. And it appears to be small. It's a property of our universe. That's what the creator has decided on the first day when he energized all this stuff. All right. His choice was rather strange dimensions, a small constant. If I were him, I would make it everything by the same order. But he had a better feeling for harmony, so he made this constant pretty small, and we will see from illustrations that it nicely separates different physical phenomena. So to recall now is that it is about 1%, 10 to the minus 2. That's why this energy accumulated in photonic fluctuations is very small as compared to atomic energy. So its contribution to energy of an atom is just 10 to the minus 6, 10 to the minus 2 to the third power. Yep.
Or summarize with the kind of delta E0, and then from a kind of arbitrary size of the atom to a fundamental constant. It's kind of with magic.
Okay, let me repeat it shortly.
Yeah.
So first of all, we have computed this one. It doesn't know anything about atoms. It's about spectrum of photons in a medium. So we have modified the velocity of light. That's why we have this difference. That's how much we can earn by modification of the vacuum. What's modification? Oh, we just placed atoms over there. Fine. That gives me certain energy density, and if I don't compare it with anything, I'm just a bit lost. I don't know whether it's big energy or small energy. So I have to find the scale. The scale is the energy of atoms which I put there, right? So I began separate calculations, similarly separate. I estimate atomic energy in terms of electronic charge, in terms of Planck constant, in terms of mass of electrons. I also computed the volume of an atom, because this is energy per volume. Fine. And finally, I compare this to and this energy per atomic volume with atomic energy. But I observe that electronic mass cancels from this estimation. And this ratio depends only on fundamental constants, which do not know, but electrons just know about our work. Elementary charge, Planck constant, and speed of light. All combined makes dimensionless quantity alpha, and that's important for the whole structure of our world, for hierarchy of different physical phenomena and scales, that this alpha is small. Right, that was 0-point energy. Let me try something else. Let me talk about uncertainties of the fields. So we know uncertainty of momentum and coordinate in quantum mechanics. Heisenberg uncertainty relation that is derived from commutation relation. These operators do not commute. That's why they obey uncertainty relation. One cannot have simultaneously well-defined momentum and well-defined coordinate. Okay. All right, we can do similar things for any physical quantity. So let me solve this problem for all possible fields once and forever. And then we can use, we can make it concrete by substituting these values for a particular field. Any operator, field operator, is linear combination of creation and annihilation operators corresponding to different modes. Let me take these operators. They're characterized by, I could say, vectors, by quantities, some quantities which depend on the mode. All right? I'm gonna compute this commutator. Right? So similar to what you do in exercises, homework, just computed this commutator. I observe that it's only non-zero for consigned modes here and here. So that's the answer. That is what is the commutator of two operators, two field operators. Let me stress that it's not an operator by itself. It's like with momentum and coordinate. It's just a constant. But this constant contains all information about the field in terms of this xk, ik. right? That is general, so I could do it for any field. Let me, since I have already taken this X and Y, let me make yet another simple calculation. Let me compute vacuum fluctuations of those quantities. Right? Vacuum fluctuations are fluctuations in the ground state, in the vacuum. One could wonder how anything can fluctuate in vacuum. Vacuum is supposed to be empty space in classical mechanics. Yeah, but apparently something does. We can compute it. Right. So what is a fluctuation in general? It's a product of two operators, correlator of two operators. For classical quantities and quantum mechanical quantities, for quantum mechanics, I have to think of order of these two operators. They don't compute. So I just put it symmetrically as a definition of quantum fluctuation. I put it symmetrically, now I can substitute those. So it is an anti-commutator. As anti-commutators of A's, run the computation K using this fact. Again, it's just applying the commutation relations which you know, commutation relations between operators A and computing all expressions for the vacuum state. Fine. So we can compute it. Here it is. Again, it's expressed in terms of X and Y. I can take the same operators. So in this case, I really concentrate on the fluctuation of X. So it's a sum of squares of fluctuations for each oscillator. Good, that's general formulas. Let me make examples. Let me make some stories about exemplifying those. Again, I want to talk about electromagnetic fields. Right, let me take as an example magnetic and electric fields. Let me concentrate on the field operators. Right. That's what I wanna get. Let me recall which formulas I want to use. Before the break, we have quantized operators. Right? So we express it as a linear combination of creation and annihilation operators. And all this for a given K just gonna be xk in this formula. And for magnetic field, I have corresponding y's. Fine. That's how I come to here, and I have some power strange expression. First of all, it looks simple in the sense that it doesn't have much elements. But right, I have some divergent sums, so I really have to think how to related in quantum mechanics terms. Good. Anyway, what I want to do is to compute uncertainty in different points. And this is given by the formula. Okay, again, I can replace summation by integration, do it accurately, and I get this expression. Big message that magnetic and electric fields do not commute, do commute in different points. If R is not equal to R prime, delta function is 0, and yeah, no uncertainty. But if we go to uncertain points, the uncertainty blows up. Good. What is the best way to understand this? It is written here. It is called regularization. And let me explain in more detail how do we come to this. In that case, we understand that we have something really bad happening at small scales. If something really bad and disgusting is happening, what do you do usually? Or what you don't do? You don't look there. You don't look there. It's disgusting. You look at a different side, or in our case, different scale. So we decide not to look at very small scales. So let us take our three-dimensional space and separate it into cells of the size delta L. And then in each cell, we're going to look at averages of average magnetic field, average electric field within the scale. And we don't look at smaller scales. We have a problem with that. All right? That's the regularization. And this regularization allows us to cope with infinities. Uncertainties are like it is written here. Uncertainties, okay, they persist within the same cell. There are no uncertainties related to different cells. But what we see in this cell does depend on the size of the cell. And if we have more and more accurate measurements, this uncertainty blows up, increases with the size of the cell. It's hardly practical to see, really to observe experimentally these uncertainties, one have to go to very small cells. Yes, please. At the moment, there are no direct experiments measuring these uncertainties, but kind of indirectly, if you believe in quantum mechanics, you believe in these uncertainties. So any prediction of quantum theory, which you can verify experimentally, for instance, scattering of particles on each other. In this sense, it gives you manifestation of these fluctuations. But it's not like you can directly measure these fields at this small scale. Right, that was uncertainty relations, and let me talk about vacuum fluctuations. Again, I apply this to formulas, apply expression for electromagnetic field in terms of creation of operators that has coefficients for each k, and I know how fluctuations are expressed in terms of these coefficients. Right, so let me compute the mean squared of electric field in vacuum in the same way. All right, I run a rather automated procedure. That's what I get. E is a vector of polarization. I have summation of polarization. These vectors are normalized, so I just can replace it by integral over case. You would not be surprised if I say that this diverges. There are so many divergences today. Yet another divergence we would not discuss here. Again, this divergence is at big K. That's because we kind of have a perverted habit to look at very small scales. Let's not look at it. So let us restrict by scales of delta L. Let's look at these cells. Then the fluctuation becomes finite. That's the fluctuation of electric field. Again, the smaller the scale we look at it, the bigger it is. What we have for magnetic field is very similar, right? Because in the relativistic theory, there is a deep similarity between electric and magnetic field. So it just differs only by factor. Good, so we understand now that there are fluctuations in vacuum. Vacuum is not an empty space. Something kind of wiggles in there. Can we measure it? Usually fluctuation is just as noise. You hear the noise, and then something wiggles. You can kind of measure the intensity of this noise. That's a very big fluctuation. Yeah? Fine. It's non-linear fluctuation, we don't treat it in the course. Yeah, very bad. I really had to make it. Yeah, you cannot measure fluctuations without hearing it, without accepting energy. Can't do that. Vacuum is just bloody ground state. You can't extract energy out of that. That's why, although these fluctuations present persist in vacuum, one cannot measure it directly, like we would measure, say, thermal fluctuations. One can only characterize these fluctuations by their effect on quantum processes, which say they change splitting of the levels in vacuum, in atom. Only indirect measurement is possible. Good. I want to play interesting game. Let us try to do an estimation similar to what we made for 0-point energies. Let me think of atoms, some solid state, some solid which is made of atoms. So let me take an atom as a cell. So instead of delta L, I would have to substitute Bohr radius, atomic size. Good, I will have some fluctuation of electric field. I have also an idea of electric field in the atom produced by the proton, which is not completely screened by electron. Right? So this is estimation of electric field in the atom. It's just a field produced by electron at the distance of the order of Bohr radius. Okay, all squared, because I look at fluctuation. Good, and now I am going to compare this to fluctuation of electric field in vacuum at this scale. I understand that it would be more infinite at smaller scales. I just take atomic scale. And I compare it with electric field in atom, and I kind of intuitively think, oh, I should have some small correction. Otherwise, I would see quantum fluctuation. Otherwise, quantum fluctuations would fill all my days, all my life. I expect it to be small, but if I substitute all these numbers, it appears to be big, and this fluctuation about 100 times bigger than what I have in that time. Right, so something goes terribly wrong. And it's interesting to contemplate what is going wrong. I would not put it as a control question, but it is about rather straightforward thing. The estimation which we made was for instant fluctuations. In fact, fluctuations of that kind are not stationary. Those are fluctuations of oscillators, so they can oscillate with corresponding frequencies. And what we did, we just take certain time moment and took all possible fluctuations with all possible frequencies. So perhaps it is a better idea not to restrict integration by large scales, but rather restrict frequency. So there will be the same integrals of a chi, but we don't cut it at atomic size. Rather, we cut corresponding energies at atomic energies. All right, what is the reason for that? As I told you already some time ago, atoms have their own time scales corresponding to typical energy difference between the levels, and they just don't feel electric fields with frequency which is much higher than this energy difference. It's a kind of innovative object. You cannot, as electron, and you cannot make this electron to move that fast, right? Which means that in these expressions and these integrals for fluctuations, I really have to cut at frequencies rather than at wave factors. Good. If I do so, I'm back to sanity, at least for this lecture. which is about to end. I'm back to sanity because I see again this vector of alpha to the 3. So in fact, the fluctuations which atoms can feel is like 10 to the fluctuation squared. If I just look at fluctuation, I would have a factor of 10 to the minus 3. So quantum electric fields at atomic scale is about 10 to the minus 3 of typical electric fields in. Right, I guess done. I also only need to recall the simplest oscillator possible, which I had in the end of lecture number 6. We've been talking about classical oscillator, single mode. What will happen if I connect capacitor and inductance, right? Remember, we got the Hamiltonian, where generalized coordinate, generalized momentum was expressed in terms of the current and in this coil and charge at the plates of the capacitor. Good. With these expressions, we can easily quantize our oscillator. Right? We can express operators of voltage as a capacitor, operators of current in the coil. Again, with this ugly coefficient. So ugliness seems to be invariant constant in all these expressions, but well, they incorporate all relevant physics. Now we see capacitances and inductances in these expressions. All right, what we can do with this, just repeat what we did for general electromagnetic field. That's 0 point energy of the oscillator. There's some uncertainty between voltage at the capacitor, current in the coil. All right, and there are also vacuum fluctuations. Good. It's a form. Yeah. You also have some. It has it works, if I'm not mistaken, at 2.1 giga, one of the most important ranges. To pick up the signal, it has to contain the oscillator made from inductance and capacitance. It's not really coupled or wire, but something like that. There must be something like this in your phone. Right. So if you want to have some quantum fun, estimate amplitude of quantum fluctuations in your phone. All right, with this, thank you for your attention.